This is one of a series of videos that we did for DesignCon 2019 on various topics. This particular video is on model-free analysis. And when I say models, I mean models provided by your IC vendors. So unfortunately, we don't end up simulating everything on our design. Some folks don't simulate anything on their designs, and there can be a lot of reasons for that. Lack of expertise, lack of time in the schedule, but a lot of times it's a lack of IC models or data that you need from your vendor. Even if you can get those models, they may not be timely enough, or they may have bugs that you need to work through with the vendor. And unfortunately, we still have to generate designs and make the appropriate design trade-offs. It turns out there's quite a bit of analysis you can do and checks you can do in order to verify that your design will work correctly without having to rely on those models from the IC vendors. And that's what I'm going to talk about in this video. So there's three different things that we're going to look at: design rule checking and analysis of both DDR4 and SerDes interfaces. So design rule checking is done in our Hyperlinks DRC tool, and it can check for things like local stitching vias and other items that are common in designs. So we have rules that are built into the tool, as well as you can customize your own rules. So there's a very powerful geometric engine within the Hyperlinks DRC tool. So for DDR4, we can check for things like typical topology routing, as well as things that might be common to any bus, like making sure that your trace has the proper referencing and the proper impedance, that any signal vias have the appropriate transition vias, looking at things like differential impedance and diff pair routing, and all of these get explained in the DRC help file here, and then when you run them, you can actually see the violations within the tool. On this design, it took about 4 minutes to run all of these design rule checks, and as we scroll through, you can see the different violations. So that was a stub that was too big on the flyby routing. Here's some signal vias without nearby transition vias. Here we're doing a differential impedance check. So we found where our diff pair broke apart, which of course raises the impedance. And there's some of those. There's some asymmetrical diff pair routing. And a lot of these are really easy to fix as long as your layout personnel knows about them. So once you get them notified, they can fix them fairly easily. Here's a signal going over too close to a mounting hole, so it's going over a void in the plane. Here's some differential phase violations that we found, and all these can be spit out to a report that can be sent to your colleagues and your layout personnel. Now, another thing that you can do for DDR4 designs is actually run an analysis, and of course you need to do that in order to figure out what kind of timing margins and eye diagrams that you're going to have. So in Hyperlinks, we do this in the DDRX wizard. The inputs are IC models from your vendor, timing parameters from your vendor, and of course your design or your layout. You can analyze DDRX in the pre-layout phase, but a lot of people do it once they have their board laid out and designed. And then the outputs are going to be a number of reports, as well as waveforms and eye diagrams. So without all of the inputs, can you still generate these results? And the answer is yes, you can. So we actually have a generic IBIS modeling kit for DDR4 that generates generic IBIS models for the DRAM and controller. And what those are made up of are some kind of generic I/O files that kind of assume the VT and IV curves of typical DDR4 signaling technology. So in this design, I have a controller with 4 DRAMs down. I'm going to go ahead and select the address net. And the reason for that is that my script has a couple options for applying models. I can apply models based on the selected net, or I can just assign them to reference designators. So here I've chosen the selected net, which is the reason I selected the address net, because it touches every different component in that DDR4 topology, and it automatically assigns those models to those nets. And it uses the kind of a flexible net naming convention to figure out which of those models to apply, and applies those kind of generic technology uh, models to the different pins on all the DDR4 nets. I can also apply models by reference designator. So if say I have a controller model but not DRAM models or vice versa, I can select and do it by reference designator. Now, once those models are applied, I can go through the DDR4 wizard and do my setup for speed and what type of DDR it is. Set up which are my controller and which ref-deses are my DRAMs. Set up the configuration. Again, this design just has 4 DRAMs down, so it's a single rank config. And then based on how those generic models were applied, I can go ahead and pick which of the nets I'm going to simulate, and it's going to map based on the pins what signals map to which net names. And so once I have that set up, I can choose which nets of the ones I selected that I want to simulate. So in this case, I'm just going to do the first byte lane, the first 8 bits, and the associated DQS strobe signal. Our generic models also have ODT models. So if you get a model from your vendor, these are typically going to be in the model selector keyword within that model. And so there are different I/O models for the different ODT configurations. So I have different ones for my controller and my DRAMs. And once I set up one DRAM, I can apply the settings to all the other DRAMs. And so that makes it kind of easy to go through. And you'll find that this wizard is generally easy to set things up. Last thing I need to do is set up my timing information. And again, if I can't get that information from my vendor, I can use our ideal timing, which describes the relationship between the timing relationship between all the signals, so that you're getting a worst case timing that's gonna show up in your results and give you what your margins are going to be. So here I've generated my eye diagrams for both the write and the read cycle. For the read cycle, there's no eye mask because, again, we're at the controller, which isn't governed by the JDEC spec. So there's no eye mask there, but you can see we have a nice open eye at the receiver at the controller. Now in the write cycle, where we're driving to the DRAMs, here we have an eye mask because that is driven by the JDEC spec. The DRAM iMask is in there, and then here we can see, as we might expect, things don't look quite as well on the write cycle, but we still get our results. And if we compare that to what the simulation would look like with the actual vendor-specific models, we do get very similar results. So I was able to actually get those results without having to rely on a vendor model. Now, doing model-less analysis is kind of a growing trend in the SerDes realm. Here I have a 100 G-base KR4 Ethernet link where I have multiple drivers and receivers set up, and the method of checking compliance on that is actually channel operating margin, or COM. which makes some assumptions about drivers and receivers and doesn't actually rely on you getting models from an IC vendor. So in this topology that I've set up here, I have a connector model modeled with an S parameter. I have all my trace transmission line models, and then I also have some via models. Now you can use our built-in simple via model or use the 3D field solver, which for anything of appreciable speed, you of course want to use the 3D field solver. It's useful for any kind of non-regular structure like vias. And I was able to configure those completely in the what if analysis environment in line sim and set up that 3D model. And then it will solve and generate an S parameter model that gets used in the simulation. So when we open up the compliance wizard here, it's pretty simple to go through that setup, and it's going to run that COM analysis or channel operating margin analysis, which again is making some assumptions about the driver and receiver. It's kind of assuming its own models, and it comes up with a single metric at the end. And you can see that we passed on all of our channels that we simulated here. We also get some additional information like idealized taps, our insertion loss and return loss plots, as well as things like an impedance plot, which I think is incredibly useful for quickly spotting impedance discontinuities and helping you troubleshoot problems with your link. We also generate eye diagrams, which aren't part of compliance for Ethernet, but they give you kind of a qualitative view of what that signal is looking like. And so that was all done in the pre-layout phase. Once we have an actual design, we can open it up and do some checking in Hyperlink's DRC, similar to like what we did for DDR4, only here we're doing it on Ethernet. Here we found a differential impedance violation, which would be tough to spot visually, but with the built-in electrical check, it'll actually figure out what that differential impedance is. Also found a asymmetric via configuration there and flag that. You can also do analysis with a completed design. In fact, here I've set up a multi-board design where I have both my line cards and my backplane connected by connector models. And so I have that entire multi-board configuration set up in board sim. And so once I select a net, it selects it all the way through. And then it also automatically finds any areas needed for 3D analysis. Again, this is a very powerful feature. It basically finds any of those irregular structures like vias or these DC blocking caps and automatically generates a 3D model that will get sent off to the 3D solver and solved, which then gets used in the analysis. So when I run through the compliance wizard here, it's running with accurate models for everything. And here I actually have some failures on some of my links. I have that same additional information, the different tap settings, as well as the insertion loss plots and the return loss plots. And here we can see a little bit worse results than before, if you remember those results from before. And you can even see it in the impedance plot there. I have some really strong dips, probably due to some excessive via capacitance. And so if we look at the eye diagram, again, strictly qualitative, but you can see that there was a big difference with the eye diagram that we ran before. And all this I was able to do without really even talking to my IC vendor. Of course, it's best to get models from your IC vendor and get the most accurate simulation you can for sign-off, but there's still, as you can see, a lot you can do to verify the performance of your design and make sure that you're making the right design trade-offs, all without getting models from your vendor. So we can kind of see that doing model-free analysis is really practical and useful.